is active learning of GAV schema mappings, and the talk is going to be given by Kun Qian.
Okay. Thanks for coming. My name is Kun. I'm from IBM Research. Today I'm going to talk about our work on active learning of GAV schema mappings, and this is a joint work with Bowder, Tengkat, Fokyeong Kalaitis, and Wang Chu Tan. Actually, an earlier version of this work appeared in my PhD thesis. Okay, so on Monday, Fokyeong gave a gym talk on schema mappings and data exchange. So I assume now you already have some basic understanding of the concepts. So here, just a quick review. Schema mapping is usually denoted by a triple, M equals S, T, and sigma, where sigma is a collection of high-level assertions that describe the relationship between a source schema S and the target schema T. And the data exchange problem for schema mapping M equals S, T, and sigma is the following problem. Given an S instance I, our goal is to find a solution for I that is a T instance J, so that Ij satisfies sigma. So in fact, actually, we prefer universal solutions because, as mentioned in the gym talk given by Fokyeong, universal solution is the most general solutions and with several good properties. So the standard language for schema mappings is the language of GAV constraints. So GAV stands for global and local SVU, and which is a first-order logic formula of this form. As you can see, it's an implication constraint, where the left-hand side is a conjunction of atoms over the source schema S, and the right-hand side is a conjunction of atoms over the target schema T. And here we have an example of a GAV constraint. And GAV schema mappings have two important sub-languages. First, we have the GAV schema mappings and the LOVE schema mappings. And GAV stands for global as view. The difference between a GAV constraint and a GAV constraint is that in a GAV constraint, the right-hand side is a single relational atom, and there's no extensionally quantified variables. And the difference, LOVE stands for local as view. And the difference between a LOVE constraint and a GAV constraint is that in the left-hand side of a LOVE constraint, there's only a single relational atom. Right? So our work focuses on the schema mappings that are expressed in the language of GAV constraint. So in recent years, example-driven schema mapping discovery has received a lot of attention. The central task of this problem is trying to derive a schema mapping from a given set of data examples, and where a data example is a pair Ij that satisfies sigma. And several frameworks have been introduced, in particular in 2013, Tengkat, Dalma, and Kalaitis introduced the learning framework, and which casts the problem as a computational learning problem. And in this work, they also designed an exact learning algorithm for GAV schema mappings that uses equivalence queries and the labeling queries. And in addition to learning framework, we also have several other frameworks, including the fitting framework introduced by Alex et al. In 2011. And the focus of this framework is trying to solve the fitting decision problem for GAV and GAV schema mappings. And actually, practical algorithms were designed for GAV and GAV schema mappings. And in our work, actually, we used the algorithm for GAV schema mapping as one of our baselines. And then we also have the repair framework, which was introduced by Gottlob and Sennelar in 2010. And in this framework, the authors proposed a cost model to measure the quality of the schema mappings. And following the work, Fokyeong, Bowder, Wang Chu, and myself, we designed a log-n approximation algorithm for a restricted subclass of LOVE schema mapping. But so far, no practical algorithm was designed for GAV schema mapping. And more recently, Bonifat et al. In 2017 introduced this interactive mapping specification method. And in this method, a human user is involved in the generation of schema mapping. But however, the schema mappings obtained from this framework provide no theoretical guarantees. Right? So before providing more details about our work, let's think of some practical scenario. Imagine I will have some black box implementation of some GAV schema mapping. And we can also construct source instances by collecting facts from some source tables, and then the black box can convert the source instance into universal solutions, right? A natural question we may ask is, can we reverse engineer in the schema mapping hidden in the black box? Namely, can we recover the specification of the schema mapping of the black box? It turned out that this motivating scenario can be viewed as a learning problem in the learning framework, which assume that there's a Go schema mapping that whose specification may be learned up by asking queries to oracles. So in the work done by Tomcat, Dalma, Collitis in 2013, they studied the learnability of GAV schema mapping. Actually, they showed that GAV schema mappings are efficiently learnable with both equivalence and labeling queries. So in this work, they assume that there are two oracles. One is the equivalence oracle that can answer the following question. Given two schema mapping, M and M star, check if M and M stars are logically equivalent. If not, a counterexample is returned. And they also assume there is a labeling oracle that can answer the following question. Given a source instance I, return a canonical universal solution J for I. Here, the canonical universal solution J can be obtained by, basically is the chase result of using the source instance I and the Go schema mapping. So in addition to the theoretical results, they actually design a concrete algorithm which we call exact GAV, learning algorithm for GAV schema mapping. So, but when we try to implement the exact GAV learning algorithm, we found that it's very hard to implement. Because remember that they assume that there's two oracles. One is the equivalence oracle, the other one is the labeling oracle. In our motivating scenario, the black box can be served as the labeling oracle, but for the very powerful equivalence oracle, it may not be available in practice. So to solve this problem, we designed an active learning algorithm, which we call GAVLearn. And the main characteristics of the algorithm are the following. First, it is adapted from the exact GAV learning algorithm, and it assumes that there's a labeling oracle is given by a black box implementation. And third, it replaces the equivalence oracle with conformance testing. So basically, the idea is that instead of answering the equivalence queries exactly, we use a set of universal examples to approximately answer the question. And also, GAVLearn is an active learning algorithm in the sense that the learning is done by actively doing experiments with the black box and the intermediate GAV schema mappings. And finally, we verify the usefulness of GAVLearn through extensive experimentation. Right. Okay, so here we give the pseudocode of the algorithm, but due to limited time, I won't go through the detail of it. Instead, I will just describe the key ingredients of the algorithm. So first, the input to the algorithm contains G, which is a black box implementation of the Go GAV mapping, and E is a set of universal examples for G. In practice, E may be obtained from domain experts or randomly created. For example, remember in our motivating scenario, we have this black box, right? We can then randomly create source facts to form a random source instance. And then we can use the black box to convert the random source instance into the corresponding universal solution. And then we have the random examples. And that's the input to the algorithm. The output is GAV schema mapping H that fits E and whose size is at most the size of G. So it turns out that the set E of universal examples plays an important role in our algorithm because we use it to do conformance testing. So the basic idea of conformance testing is that we use E, which are basically observations of the data exchange behaviors of the Go schema mapping G, to check whether the data exchange behavior of H conforms to the specification of G. So in particular, we think H semantically conforms to G if H and G agrees on E. Otherwise, there is an example, IJ in E, on which H and G disagree. And this example is considered to be a counterexample. So, I'm sorry?
What would it mean for H and G to disagree on this example?
So if we have the set of the E contains a set of universal examples, right? For each of them, we can chase the source instance with respect to the two schemas to see whether they generate the same target instances. If they generate the same target instance in all the cases, then we think they are H semantically conforms to G. So this is the conformance testing. So if there's a counterexample we found during the conformance testing, then we have the active learning process to extract a critically sound constraint from the counterexample. And this process relies on actively doing experiments with a counterexample we found during the conformance testing and the black box implementation. Right. Here, the critical sound constraint means that first, the constraint is sound with respect to the Go schema mapping. Namely, this constraint can be logically implied by the Go schema mapping. And it is critically sound means that if we remove one of the atoms from the left-hand side of the constraint, the newly obtained constraint is no longer implied by the Go schema mapping. So GAV also has several nice properties. Actually, we show that GAV is an optimal algorithm for GAV schema mapping. Here, optimal means that if we are given a set of A of universal example for some hidden Go schema mapping G, GAV is guaranteed to produce a GAV mapping H that is consistent with E, and the size of H is at most the size of G. And because there's a result shown by Bloom et al. In 1987 that outcome learnability implies packet learnability, so we have that GAV is also a packet learning algorithm for GAV schema mappings. Again, it means that with sufficiently large number of random universal examples, GAV will produce a GAV mapping that is approximately correct with high probability. All right. So next I will move to our experimental evaluation. So first I would like to describe the methodology we used in our evaluation. So basically, we assume that we are given a black box implementation of some Go schema mapping G, and we are also given a set of universal examples for G. And then we split E into half training set and half a testing set. And then we run GAV on the training set to generate some GAV schema mapping H, and then we evaluate the quality of H on the corresponding test set. Yep. So the metrics we use in evaluation are precision, recall, and F-score, and we define them using the standard definition. So F-score is 2 times the harmonic mean of precision and recall, and in order to define precision and recall, we first need to define false positive facts and true positive facts and false negative facts. So we define them as follows. Assume that we have a text example ij, and H is the schema mapping returned by the algorithm. Then we can chase I with respect to H to generate some target instance J prime. And then we can compare J prime and J. So then the false positive facts are those facts that are contained in J prime but not in J. And true positive facts are those facts that are contained in the intersection of the two instances. And the false negative facts are the facts that are contained in J but not in J prime. Based on those concepts, we can use the standard definitions for precision, recall, and F-score. Note that in our work, we do not report precision values because the mappings returned by our algorithm is guaranteed to be sound with respect to the Go schema mapping. Namely, the mappings will always have 100% precision. And we actually have a proposition to show this in the paper. Okay, so the schema mappings and the data examples used in our evaluation were generated by iBench, which is a state-of-the-art benchmarking tool for data integration tasks. And in our evaluation, we created 3 different types of mapping scenarios, including simple, moderate, and complex. And for each mapping scenario, it contains 3 different types of constraints. And the characteristics of the mapping scenarios are summarized in this table. So intuitively, we increase the complexity of the schema mapping scenario to test the effectiveness of our algorithm. And for each schema mapping, we also generate different size of universal examples and split them into half training and half testing set. So first, this is a standalone evaluation of GAV-learn, and the table shows the results of running GAV-learn on complex scenarios. And here we highlight the F-score results. Here, as you can see, that the F-score of the mappings returned by our algorithms are very high. In all cases, the F-score are above 90%. In many cases, it's even 1 or near 100%. So this shows that the algorithms is highly effective to find the very high quality result, schema mappings. And we also observe there's a strong correspondence between the number of training examples and the runtime of the algorithm. And this actually conforms to our expectation because the size of training examples determines the number of oracle calls that we issue to the black box. So we also compared GAV-learn with other existing algorithms that can be used to derive GAV schema mappings. The first one we consider is GAV-fit. So GAV-fit is the fitting algorithm for GAV schema mappings, introduced in the work done by Alex, Tuncav, Colaitis, and Tan in 2011. And the other one we consider is Talos. So it's a reverse engineering algorithm for union of conjunct queries, which is done by Tranatel in 2014. Remark that union of conjunct queries can be viewed as a GAV mapping because if you look at the GAV constraint, the left-hand side is basically is a conjunct query over the source instance, and the target instance is actually the results of the conjunct query over the source instances. So I also want to mention that both baselines here have only one input, that is the pre-existing set of universal examples. So here's selected results. We can see that the black lines with diamond markers are the F-scores achieved by the mappings generated by our algorithm, and the blue lines and the red lines are the F-scores of mappings returned by Talos and GAV-fit. Clearly, GAV-learn outperforms Talos and GAV-fit. And actually, we look into the mappings returned by Talos, and we found that they actually suffers from overfitting issue. And the main reason that GAV-learn is much better is because GAV-learn is an active learning algorithm that can generate more informative examples during the learning and guide the system towards a better mappings. So to verify that, we actually did an additional experiment where we give GAV-fit and Talos the examples generated by a run of GAV-learn. And here's the brown lines. Actually, is the modified the F-score of the mappings returned by the modified version of Talos. And here we didn't plot the F-score of the modified version of GAV-fit because the F-score of GAV-fit in the modified version actually coincides with GAV-learn. So as we can see that by given GAV-fit and Talos, the examples generated by GAV-learn, both algorithms can perform significantly better, which also shows that our algorithm actually is very effective to find informative examples during the learning.
Can you tell us what the x-axis is here?
Oh, right, sorry. So that's the number of size of a training set. So we increase the size of training set. Right. Okay, so as a conclusion, we designed a GAV-learn algorithm, which is an active learning algorithm. That is adapted from an earlier exact learning algorithm. And GAV-learn provides theoretical guarantees, and we experimentally showed that it is very efficient and effective to learn high quality results. And we also learned that from this study, we learned that we think that conformance testing can be a very good substitute for an equivalence oracle that is usually required by many exact learning algorithms. But for the future work, right now the exact learnability of GAV and the LAV schema mappings are still open, and we don't know whether we can design similar active learning algorithms for LAV and GAV. Thank you. Yeah. So actually, first for the training examples, we consider like 5, 15, 13, and 45. And in each examples, there are more details in paper, but it ranges from one example may contain 10 facts, and the largest one may contain like 200 facts.
So a very small database.
Very small, but yeah.
Yeah, I was wondering if you have been able to compare your work against active learning in inductive logic programming, because in inductive logic programming they have also algorithms that tries to learn a data log program, data log query by active learning. Actually, Cardon from Top University, I suppose, they have an open source basically software that does it. It implements the exact learning to learn data log programs, which I think is better baseline.
Okay, could be, but because here we focus on the algorithm that can derive GAV schema mappings, we actually, I think we can consider that in the future. Yeah, thanks.
Yeah, more of a comment or something interesting. When you, I think if I understood correctly, the conformance testing, when you say that you find a counterexample, in the real world when we generate mappings and we see that something doesn't work, it's not because the mapping was wrongly realized, it's because it was a data quality issue.
Right.
So it would be interesting to say, make the problem a bit more complicated and say, oh, I don't know, is it actually is it a counterexample or is it actually probably the data in the mapping is correct?
Right, that's true. Because in this, in our assumption, we assume this the black box. I mean, we don't assume there's a data quality issue. We think data is relatively clean. Actually, it's clean data because we have the universal system. Yeah, that would be interesting if the data is not.
Probably
Yeah.
more complicated.
Yes,
That would
yes,
be really-
definitely.
That's a real world. That's what I see in the real world.
True. Yeah, thanks.
Is there a connection between learning UCQ GAV or UCQ, learning DNF formulas? And again, people have looked specifically at learning formulas that are in disjunctive normal form. UCQ is essentially a disjunctive normal form of some sort. Is there a formal connection?
Formal
There
connection.
are results about learning DNF that are better than learning general Boolean formulas.
Okay, that could be. If you're learning DFH.
Yeah, but it could be that there is concept for lifting. People have looked in concepts of cognitive, about how techniques from grounding, there is something concept for lifting. So it would be interesting if there is a connection between the DNF learning and UCQ learning. Is UCQ learning somehow lifting or DNF learning?
Yeah.
The resolution was a fine example of lifting, right? From propositional resolution to general resolution, which included the concept of not general unifying.
Yeah, it could be an interesting direction. Yeah.
I have one final question. So,
Sure.
are you generating when you find the constraints are unsatisfactory? Is there any specific way you choose the counterexample? Because in active learning, there are techniques you choose, like the more controversial example or the example that's going to help you cut the space more efficiently. Do you do it in a particular way? Do you choose a random example? How do you do that?
So the basic idea is that actually more details can be found during the poster section. But the basic idea is if we have a counterexample, then the active learning in our algorithm we believe that we can simplify the counterexample into a constraint by systematically removing facts from the source instance. We'll find by active learning, the goal is to try to remove facts from the left-hand side, from the source instance, and keeping everything in the target, so that once we simplify, we'll have we can extract the constraint from the source instance, basically. Yeah, we can discuss that offline. We have an example in the poster to show that.